Hello everyone, my name is Nadeem and my partner is Marco. In this short video, we'll demonstrate how we determine the damping ratio of a stainless steel ruler acting as a cantilever beam. We'll also compare our experimental results to theoretical continuous system predictions. Here you can see our setup. It's a 12-inch stainless steel ruler clamped to the edge of a table, leaving about 10 inches free. We gently pulled the tip downwards and released it, displacing it about 10 millimeters and letting it vibrate freely without any external force. We filmed this motion at about 60 frames per second using a phone camera placed level with the tip. You can see here that I've imported the video into Tracker. I set the coordinate axis so that the origin is right on the initial position of the ruler tip before displacement. I then calibrated the scale using the distance from the initial position to the displaced position and telling Tracker that that amount of pixels is 10 millimeters. Then I created a point mass tracker and I manually tracked its position frame by frame at the ruler tip. This gives us displacement data versus time, which I then exported to Excel for the analysis. Here is the clip showing the tracker in progress. It was about 1.5 seconds of motion, and you could see here in the graph with time versus the y displacement that over time that distance, the oscillation is dying down due to damping.
After we captured the motion in Tracker, I worked on analyzing the results and visualizing the damping behavior using MATLAB to calculate how the vibration decays over time. Here in the Tracker, you can see the vibration pattern of the ruler tip, each peak gradually getting smaller, which shows the damping effect as the ruler loses energy with each cycle. We exported this displacement data into Excel so that we could use it in MATLAB to further analyze the data. So here you can see on the Tracker data, it shows all the peaks of the graphs and the data that we were able to export into an Excel. And then now to get into the graph. This is the displacement versus time graph that we created in MATLAB. The blue curves represents the measured motion, and the red dots highlight the main peaks amplitudes that we calculated using MATLAB. The downwards trends and the peaks clearly show how the vibration amplitude decays, confirming that energy is being lost over time due to dampening. From these peak in MATLAB that we calculated using logarithmic decrement of about 0.22 and a damping ratio of about 0.035 or roughly 3.5%. These numbers mean that each vibration cycle loses about 3.5% of its energy, which is typical for a stainless steel vibrating in air and matches what we would expect in theory. And to go into our code, the first section imports the time and displacement data that we got from the Excel. And the next portion applies these formulas that we've learned, the logarithmic decrement and the dampening ratio, and letting MATLAB run both of these automatically. And you can see by the results printed here in the command window, confirming our experimental dampening behavior. Overall, this analyst helped us connect our real experimental data with vibrations theory we learned in class. Using MATLAB made it a lot easier to visualize the dampening effect and confirm that our measured values align well with the theoretical expectations for a cantilever beam. Thank you.